Kinetic energy, often abbreviated as Ke, is the energy possessed by an object due to its motion. It is a scalar quantity, meaning it has magnitude but no direction. Kinetic energy is fundamentally tied to the object's mass and velocity. This energy represents the capacity of a moving object to do work on another object upon impact or interaction, for example, a moving hammer driving a nail. The quantitative expression for the translational kinetic energy of a point mass, or a rigid object moving without rotation, is Ke equals 1/2 mv squared. Here, m is the mass of the object in kilograms, and v is the instantaneous speed of the object in meters per second. Key implications of this formula include mass dependence and velocity dependence. Kinetic energy is directly proportional to mass, so doubling the mass doubles the kinetic energy provided velocity is constant. But kinetic energy is proportional to the square of the speed, so doubling the speed quadruples the kinetic energy. This explains why high-speed collisions are dramatically more destructive than low-speed ones. Another important implication is frame dependence. Kinetic energy is measured relative to an inertial frame of reference. An object has different kinetic energy values in different reference frames. For example, a ball thrown inside a moving train has different kinetic energy relative to the train versus relative to the ground. The work-energy theorem provides a crucial link between kinetic energy and the concept of work. It states that the net work done by all forces acting on an object is equal to the change in its kinetic energy. Mathematically, net work equals change in kinetic energy, which is kinetic energy final minus kinetic energy initial, or 1/2 mv final squared minus 1/2 mv initial squared. The work-energy theorem is powerful because it directly relates the net effect of forces, meaning work, over a displacement to the change in the object's state of motion, its kinetic energy. It applies regardless of whether the forces are constant or variable, which simplifies many dynamics problems. It also highlights that positive net work increases kinetic energy, meaning the object speeds up, while negative net work decreases kinetic energy, meaning it slows down. Understanding kinetic energy is essential for analyzing systems using the principle of conservation of mechanical energy, which applies when only conservative forces act. Here, the sum of kinetic energy and potential energy, including gravitational and elastic potential energy, remains constant. Energy transforms between kinetic energy and potential energy forms as an object moves. For example, a falling ball loses gravitational potential energy and gains kinetic energy. This video about kinetic energy is part of our larger Physics 1 for Engineering students course. The course is entirely free and has more than 100 subtopics inside it. We're excited for you to try it, and the link is in the description.